How about I do this? I'm going to do you one better. I want to try and answer that question by being not just generic, but being specific. So, in order for the video to make a little bit of sense, somebody asked, how do I know whether to use 0 degrees or 180 degrees? The barbell example was the example in question. Let's be a little more open about that. Let's talk about any of the angles that might be used. So here's something, okay? And so let's say there is friction. Let's say there's a kid here and they're pulling on the box. And a littler kid here and they're pulling on the, they're also pulling on the box. That's not what I want. They are pulling on the box. Okay? But let's say the box goes this way. Some change in position. We'll call this force 1, force 2, and there's friction. Look, there's a lot of forces acting on the box. A free body diagram would suggest that there's force 1, there's normal force, there's weight, there's force 2, there's friction. All these forces are acting on the box. Well, which ones do work? Well, all of them could. Now, to really answer the question and talk about that angle, the angle in the definition of work is the angle relative to the displacement. So that makes this 0 degrees. Every other force is relative to the displacement. So force 1, I would need this angle to be able to calculate the work done by force 1. For the weight, I would need this angle. This one right here, which is likely a right angle. For the normal force, I would need that angle, which is also a right angle. For the friction, I would need that angle. That would be 180 degrees because the box is moving to the right, but the friction would be to the left. And for force 2, I wouldn't need this angle. I would need that angle. Now, Lauren, does that make some sense to you? Now, this part I would really, really listen to. If you really want to understand some of this, you have to get what they're trying to get out of that cosine. They want how much of that force is aligned with the direction of motion. This means that every angle less than 90 contributes to moving the box in the direction it's moving, and every angle greater than 90 is trying to prevent it from moving. If you look in your calculator, cosines of all angles between 0 and 90 are positive, and cosines of all angles between 90 and 180 are negative. Right? You did the unit circle, so you know all that. So all quadrant 1 and 4, all positive. All quadrant 2 and 3, all negative for cosine. So generally what they're trying to figure out is how much of the force is trying to get the object to move in the direction it's moving, and those should be positive numbers. The cosine is telling you two things. How much of that force is pushing it in the direction it's going? And is that force making it go that way or trying to prevent it from going that way? That's what the cosine's about. So when you're talking about lifting the barbell, all right, well, the barbell, has, two forces acting on it when you're trying to make it go upwards. So if I'm trying to make the barbell go from here to here, I could think of two forces acting on it. Gravity for sure is acting downwards, but you're pushing it upwards. Your force is in the direction it's moving. It's cosine of 0 degrees. Gravity is against the direction you're moving. Cosine of 180. You do positive work, gravity does negative work. It's hard to think of gravity doing negative work, but remember, gravity's trying to prevent the bar from going up. So it does negative work. In the same way, once the bar is up there, and you're going to let it come down. So now we're moving this way. That's the delta x. You're bringing it back towards you. Gravity is going to do that all by itself. You're not necessary. You let go of the bar, it'll come down. Promise. So it does positive work. Your upward force does negative work. Why? Because if you don't do that, there'll be a change in kinetic energy of the bar. You're trying to prevent it from hitting you. So you push up to make sure that the work done by gravity doesn't change the object's kinetic energy, so that it comes down in a controlled fashion, and therefore you don't kill yourself with that bar. A cable lowers a 900 kilogram elevator so that the elevator speed increases from 0 to 4 meters per second in 6.1 meters. What is the force that the cable exerts on the elevator while lowering it? And I believe it's part B that asks something weird here. What is the force that the cable exerts on the elevator while lowering it? Assume that the system is the elevator only. And the other one, assume that the system is the elevator and the earth. All right, so I find that to be a weird question. But let's just take the problem at face value about what it's asking. Somebody asked about it after school, and here's what I told them. The elevator. Can we all recognize that for the elevator to accelerate downwards, there's got to be the force of gravity downwards and the tension upwards. It is a 900 kilogram elevator. And we are told that the object's velocity starts at 0 and becomes 4 meters per second. And your values may change because I did not use uniform values, so you might have different numbers. But it tells me that the delta x was, it says 6.1, but I'm just going to do 6. Okay? Any questions before I get started? All right. Here's what I think they're trying to get at. Now, just so you guys know, I'm not going to do this on the exam. All right. If we're near the Earth, gravity is the force on the system. If I don't want gravity to be a part of the problem, I'll use horizontal forces on it. Okay? But let's just go with the problem as stated. I know that the net work on the elevator has got to be equal to the change in kinetic energy of the elevator. Now, there's options for how I do this problem. I want you to understand there are options. I could use conservation of energy if I wanted to. It would be harder because I have an external force in the system acting on the system. That external force is taking energy away from the system. It is preventing the elevator from having all of its energy converted to kinetic. So it really doesn't fit the mold. Work would be the better way to do it. And from the standpoint of the elevator, I see two different forces that do work on the elevator. There's the work done by gravity and the work done by the tension, and those have to sum to give me the change in kinetic energy. Gravity acts down and the elevator goes downwards. So the work done by gravity, 3 bins here, will be mg times delta x times the cosine of 0 degrees. At the same time, there's the work done by tension. Tension is upwards. Delta x is still downwards, but that's going to suggest then that the tension is doing negative work on the system. Why? Well, the tension's keeping the elevator from speeding up too much. Either way, there's a change in kinetic energy of 1/2 m4 squared minus 1/2 m0 squared. Any questions yet? All right. I'm just going to use 10 for G so I can make this quick, but you guys know that mastering is going to want 9.8. So I've got 900 times 10 times 6 times 1. That is the work done by gravity. Plus T times 6 times -1. That is the work done by tension. Equals 1/2 times 900 times 4 squared. This will give me the tension. Now, I don't care what the number is. You can do the number part. This is just algebra. That's not that big a deal. In the next question, it asks, what is the force that the cable exerts on the elevator while lowering it, assuming that the system is the elevator only? The problem with that is that I can't lower the elevator with an upward tension. You follow me? I can't. So the question doesn't make a lot of sense. And so I don't fully appreciate it, like what they're trying to get at. What I would recommend you consider is that the tension force, if I'm not considering the Earth, would be the force that would cause the change in kinetic energy. So the only way I could bring the elevator downwards without considering the Earth as part of the system is to assume the tension is what lowers it downwards. It's the only way. However, that's not what they do in the answer sheet here. In the answers here, they still use the force of gravity on the elevator to get their answer. So I don't really know what to make of part B of this question. When I read it and assigned it, I was mostly interested in part A. I thought that part B might have been actually speaking to what the net work done on the elevator was, which is what I would ask if I was writing this question. And I must have read it too quickly. Does that make sense? Because the net work done on the elevator would just be whatever this is, which is 1/2 times 900 times 4 squared. So if I was writing a test, I'd ask that question. But them asking about with the Earth and without the Earth, I think is misleading. So how about I just kind of draw this and tell you about this problem, since I had to do it yesterday after school to a group of people who just had to hang out. It was a lot of fun. That's why people were already asking about hanging out. I'm like, look, it's not really hanging out if we're here just doing homework. So it'd be better if we could meet at like Starbucks. That would be better. I mean, we could, but... Ooh, so pretty. All the pretty colors. Alrighty, here we go. So this is basically the situation at the start of the problem, except with one minor difference. There's a spring here. We're told that the one on the table is a mass of 6. Stop it. The one hanging off the table is 12. And just because this wasn't enough fun, there's a coefficient of friction between the blocks and the table of 0.7. And the spring has a spring constant of 300 newtons per meter. And what more fun could they add? They would like to know that once I release this, How far does it move until it comes to rest? So I think what they're trying to say, and I'll read it. It says, the spring is relaxed as the person is holding the block, but the string is still taut. When block 2 is released, it moves down for a distance d until it stops, the final state. I would assume that it stops and then springs backwards. Does that make sense? I don't think they're saying that it kind of comes down and stops and stays there. If they were, that's possible, but I don't think that's what they're getting at. I think they want to know how far the block moves. Now, the problem asks about all these potential energy or conservation of energy graphs. I don't care about that garbage. I care about you being able to tell me how far it moves, D, and explain why it stops and then comes back. So you should probably recognize that if you've been paying attention at all, that there's lots of work in this system. I would encourage you to consider looking at the idea of work here. You could use conservation of energy if you'd like, but I think it would exceed our definition of conservation of energy because of the frictional force that's here. Now, you can use conservation of energy, but you would have to understand that the energy before you release it is not equal to the energy after you release it. There's going to be some missing energy, and that'd be the energy that went into friction. And you'd have to be able to put that in there somewhere. So I would encourage you to think about it this way, that the object has the object has a final velocity of 0, so the change in kinetic energy of the object is 0. That suggests that the net work in the system is going to be 0. Now, why does the block stop? That was question A. It stops because as block 12, the 12 kilogram block falls downwards, it stretches out the spring. And eventually the spring is going to start pulling backwards on the blocks. If you stretch it far enough, the energy that was in block 12, the gravitational potential energy, will then be the energy that's in the spring, plus a little bit left over on the ramp for all the friction that was taken away. That's why it will stop. And then it will bounce backwards. And then stop again and probably go forwards. Now it'll keep going until friction has bled all the energy out of the system. Now, if you don't like that argument, then just use what we talked about in class. Let's talk about the work done by all the forces that act on each mass. Fair enough? All right. Now, I'm going to be thorough here, but you should probably understand that I'm trying to work something in that might be on the multiple choice. Name me some forces acting on the 12 kilogram block. Tension, sure. Gravity, sure. What else? Oh, so we stopped there, right? There's only 2. Now, so that means on the 12 kilogram block, there's the work done by gravity and the work done by tension. Easy enough? Let's just put those down real quick. That's going to be mg times d times the cosine of 0 degrees. You guys good with all that? So look at the 12 kilogram block. So mg, 12 times 10, times d, we don't know what that is, times the cosine of 0 degrees. Talk about the work done by tension. Do we know what the size of the tension force is? We don't. So I'll just put T. We do know that the blocks go downwards a distance D, correct? And I think we can all agree that it's cosine 180 degrees because tension's up, but the blocks go down. All right, that's it. Let's go on to the next block. Let's go on to the 6 kilogram block. 6 kilogram block. Name some forces that do work on the 6 kilogram block. Tension. So there must be work done by tension. Work done by tension. What's another force that does tension on the block? Or, I'm sorry, does work on the block? What's that? Gravity. No, it doesn't. Gravity acts downwards, the block moves to the right, so it doesn't do any work on it. Name another force that does work on the block. The spring does work on the box, sir. Name another one that does work on the block. Friction, sure. Okay. Tension. We don't know what the tension is, so I'll just have to put T there. Can we all agree that this block moves a distance D this direction? Okay, so that's going to be D. And can we all agree that the tension is in the same direction as how the direction the box goes? So that'll be cosine 0 degrees. All right, how about the work done by the spring? Yes?
Can we still use D? Do we know if it's going to be the same distance as the spring?
The only way that it wouldn't be the same distance is if the string stretched.
Okay.
So I think we're okay. So how about the work done by the spring? I actually can't do force times distance for the work done by the spring because the force isn't the same all the time. So as I said yesterday, the work done by the spring is 1/2 kx squared. I can, however, talk about the direction of this force. Can we all agree the direction of this force has to be that way? The spring pulls that way on the box, but the box moves in the direction of D? That means cosine 180 degrees. Now, I put x squared there, but I hope that all of you recognize that that's got to be D. The spring is stretched the same amount that the box moves. All right. Work done by friction is the last one left. Mu mg, frictional force. Any question about why I'm putting it there? Go ahead. Well, remember, friction is mu times the normal force. Is friction. The box has a weight of mg, and the normal force is upwards, so normal and weight have to be balanced here. That okay? Now look. All right, the whole class is leaving because they hate physics, but I'm going to keep going. And replace the mu mg with what we know it to be. It's, in this problem, we know that mu is 0.7, m was 6, and g is 10. We still don't know how far the block goes, that's D, but it is cosine of 180 degrees. Now, that's it. Add all of these together, and that has to equal 0. Now, if you're really, really looking at this, please notice that these two cancel out. The work done by tension on one block is equal to the work done by tension on the other block. It's an internal force. Internal forces don't change the energy of a system. So they cancel out. So what I get is 12 times 10, or 120 D. That's this one. Minus the work done by the spring, which is 1/2 times 300 times D squared. It's negative because of the cosine 180. Minus the work done by friction, which is 0.7 times 6 times 10, that's 42 times D. And again, it's negative because of the cosine 180. That has to all equal 0. Solve that for D, and you're done. I'm not going to do that, by the way, but that will tell you what D is. Number 20. It is a windy day, and you are moving a 18-kilogram box at a constant speed over 10 meters by pulling a rope that is attached to the box. The rope makes an angle of 25 degrees with the horizontal. The coefficient of friction between the box and the ground is 0.4. The force exerted by the wind on the box is 19 newtons. Alrighty. And a partridge in a pear tree. What other crap could be acting on the box? So, I have a box. Oops, that's not a box. Yeah. Some days I'm better doing this than others, but all of these days where I'm drawing all this stuff, you know, I've talked to other teachers now who are trying to do this. Some of them with probably great success. You know. So here we go. That's the first force. They tell me that, they don't tell me the size of this force, do they? They say it makes an angle of 25 degrees. They do tell me there's a coefficient of friction of 0.4. So they don't tell me the size of the force, but I'm pretty sure we'll say the frictional force is acting that direction. I get the idea that the wind is not helping me, but I'm not sure that's clear. So, determine the work done by you on the box if the wind is blowing towards you. So I assume that means the wind is pushing this way. Is that good? All right, so we want to find the work done by you on the box. Well, they tell me the box is moving at a constant speed. So that means the net force has to be 0. All right? Now, we've got a couple ways we can approach this problem, but none of them are particularly great. So I'm going to go with the good old work energy theorem, which I know shows me that the work done on the box has to equal 0, because there's no change in kinetic energy. Is that okay with you guys? Any question about that? Yep.
Like the total work done on the box, not the work of you, right?
Not the work of me. Now, this is not the best way. Actually, the truth is, because I need the work done by me, I'm only going to be able to get the work done by me if I know the force by me. Or I know the friction. I don't know either one of those, which is why I'm kind of at a loss. The only way I'm able to figure this out is if I know what the force is that I apply to the box. Now, the big part of this that's tough is the frictional force here. I'd love to say that the frictional force would just be mu times the normal force. And although that is true, the normal force isn't the weight of the box. The normal force is going to be, well, in this case, mg minus f sine 25. I could draw a free body diagram for you if you need to see it, but we've done this before. So I kind of feel like I should say, see that problem before. But this force is both pulling up a little bit on the box and pulling to the side a little bit on the box. The amount that is pulling up is F sine 25. That plus the normal force have to equal the weight of the box. Thus, that has to be the normal force. So, with that in mind, here we go. The work done by me is F dot 10 meters dot cosine 25 degrees. This is the work done by F. Any question about that? The work done by the wind will be 19 times 10 times the cosine of 180 degrees. Any question about that? Yep.
The 19 was the force of the wind?
Yes. Pretty sure it's what, I mean, it might be different for everybody, but mine says 19 newtons. The work done by friction will be 0.4 times mass of the box, which is 18 times 10 minus F sine 25 dot 10 dot cosine 180. Ew, that's a mess.
Sorry, does that say 19 times? I can't read that. 0.4 times
18 times 10. That's all right. You don't have to be sorry. You guys have the problem too. It's 18 kilograms. Yep. Yep.
I was just wondering where the 18 came from, but you just answered
Alrighty,
that.
keep going. This has to equal 0 when I add all of those up. Look, I'm only trying to figure out F from this. Now, I could have done this a different way. Net force equals 0. I could have figured it out that way too. right? You guys do see that, right? And by the way, that is what is here. Each one of these is multiplied by 10. That's the only difference. I've got positives and negatives. That comes from evaluating the direction of the forces. If I'd drawn a free body diagram, I would have gotten the same thing for this part of the problem. Either way, that's going to be 10 cosine 25 times F minus 190 minus, this one's going to be messy, 4 times 180 minus F sine 25 equals 0. Solve that for F. Oof. What if I don't want to? It doesn't really matter though, does it? You're going to make me do it anyways. But I think I'm out of space to do it. Do you mind if I kind of do that? That okay with all of you? Oh, I'm glad you agree. So let me see. 10 cos 25. I'm just going to collect terms because I'm better at it than you guys. So I'll do my algebra faster than you. F times 10 cos 25 plus 4 sine 25 equals 190 plus 0. 4 times 8 is 2. With the 3, 720. There you go. That's the answer. You can find F. I can't do the rest because I don't know what cosine and sine of 25 are. But you guys are likely to be able to. Now, this will not give you the answer to the problem. This will tell you what the force is that you applied. That's why I need you guys to do that. So if you would be so kind, 190 and 720 is 910. And this will not be the answer in mastering, by the way. Divided by 10 cos 25 plus 4 sine 25. You understand what we're doing right now is the least important part. It is the least interesting part. And it's too long for me to put on the test, but it's more than okay for the homo work. All right, so look. I don't want to spend this kind of time waiting on you guys. Not that it's not worth it. But when you're done here, the work will equal the force you just found times 10 times the cosine of 25. You will still have to take that force and plug it in here. Now, you could have done this problem by doing net force instead. I did it this way because this is the unit we're studying. Now, just to be aware, question B is now going to make you do the entire thing over again. But this time, you have to add the wind instead of take it away. Which means this time, this is positive and not negative. Right? It's pushing in the direction the box is going. Which means this will be negative right there, which will make this number lower, which means the force you would have to apply would be less, which makes sense because the wind is helping now. So you do less work because the wind is helping. Now, I don't want to spend any more time with you guys pushing buttons. That's not helpful. Let's try another question. Number 9 says that the tibia bone, the leg bone, connected to the arm bone, connected to the ankle bone. You jump from some distance and land on the ground, and then you absorb the impact of the ground. I'm seeing two things happening here. You jumping to the ground, and then your legs kind of compressing as you hit the ground. The person jumps from a height of 0.4 meters. Now, if we're paying attention, I would say that work is done by gravity on the person to change their kinetic energy, right? They jumped, so they had no kinetic energy before they jumped, and then had kinetic energy due to gravity bringing them down. We all okay with that idea? So the kinetic energy they have is going to be brought to zero because the ground is going to stop them. So there's the work done by gravity to accelerate them to the ground, and then the work done by the ground to bring them to rest. So the net work on the person is zero because they started at rest and ended at rest. Fair enough? So there's the work done by gravity, which will be mg times the h times the cosine of 0 degrees. There'll be the work done by the ground, which will be the force of the ground times how far they shrink or compress as the ground brings them to rest, which is what they're asking about. They're asking how much do the bones compress as the ground brings them to rest, times the cosine of 180 degrees, since the ground is pushing upwards on them, but they continue to move downwards a small distance. Now, we say the ground on them, but that's being absorbed by the leg bone, which, as I understand it, can withstand 4 times 10 to the 5th newtons. So, without further ado, that looks like M G H plus 4 times 10 to the 5th times delta x times -1 equals 0. And I rest here. You figure out delta x. Okay? This is why you should not, of course, ever land stiff-legged, even from a short distance, because I guarantee if you experience that 4 times 10 to the 5th newtons in your legs, you'll probably break them. It says you won't, but you probably will. Yeah?
So when you're doing work with the ground, that force that you have there, that's the maximum force that they can withstand, right? Okay.
Well, that's what they said. They said they'll break if you exceed any more than this. But this is why you should bend your knees a little bit when you jump. Every one of you has jumped and landed stiff-legged once accidentally. It was unpleasant, or it broke something.
I tried it to see.
Oh, you didn't. It hurts. Yeah, don't do it. Don't do it. No matter what force brings you to rest, you are going to be brought to rest in the course of a car accident. Does everybody agree with that statement? You guys don't? Have you ever been in a car accident? Will you agree that your car will eventually stop? And you, hopefully, staying part of the car system, will also stop. The truth is, if you want to experience the least amount of force, get ejected from the car. The street will bring you to rest. It might take a long distance, and you might leave a long streak of yourself on that street. Look, you guys think you're going to live forever, but the number one thing that kills you is car accidents. Inside that car, there are a lot of things that can bring you to rest. Windshield, dashboard, seatbelt, airbag. You would like to find the thing in the car that will take the longest distance to bring you to rest, because that means the smallest force. But you are going to be brought to rest. Delta K in the car is going to happen. That's why airbags are your best bet. In fact, most cars nowadays, they're designed to start bringing the car to rest before you become involved in the accident. Crumple zones. Crumple zones in the car begin the process of stopping the car, reducing the kinetic energy of the car, person, system before your restraint systems even start to take effect. But this is the equation that determines how much force you experience. That's why they measure size of the dent in the car, size of the skid mark. Your insurance company knows exactly how much each one of those should measure and can usually work backwards to figure out how fast your car was going. So it's going to be hard to lie to them about, I was only doing 20 miles an hour. They're going to know. All right, that was fun. Next question. On to see number 23.
I don't even want to talk about the kangaroo one.
The kangaroo one sucks. I don't want to do
Looked
it.
at it and I was like,
Yeah.
it was like
I shouldn't have assigned it.
It was like 11:50 and I finally got to that problem. I was like,
All right. A loop-to-loop in the Six Flags Shockwave roller coaster has a 10-meter radius. The car is moving at 24 meters per second at the bottom of the loop. Determine the force exerted by the seat of the car on a 73-kilogram rider when passing inverted at the top of the loop. All right. This could be on the exam. In fact, I would say this is actually kind of below what I would like you to be able to do. I would like you to be able to use a little more of our physics to figure out perhaps where you would have to start this ride to be able to make this happen. Yes, ma'am.
Could you flip the water back on so I can watch my ride?
This problem has two parts, and you need to see it as two parts. The first part is you recognizing that the velocity of the cars at this part of the loop is dependent upon how much energy the cars have. This seems like a clear conservation of energy problem. If we assume a frictionless track, that means there's no external force acting on the system. They are at the lowest point, so right now they have kinetic energy and no gravitational potential energy and no elastic potential energy. When they make it to the top of the loop, they'll probably still have kinetic energy. In fact, they will have to in order to be traveling in a circular path. They will have gravitational potential because they're above the lowest point, but they will have no elastic potential because there's no spring involved. Fair enough? Any question about this? The height above the ground when they're at the top of the loop is what height? 20 meters. Great. So 1/2 mv squared at the bottom of the loop has to equal 1/2 mv squared plus mgh at the top of the loop. All energy can tell me here is how fast they're going or how high they are in the loop. That's it. But the reason I need to know how fast they're going at the top of the loop compared to the bottom of the loop is because they're in circular motion at the top of the loop. They're asking about a force on them at the top of the loop. In order to figure that part out, I need to remember that the net force for an object traveling in a circle has to equal MAC. A separate topic, one from last chapter. And there are two forces acting on them at the top of the loop. There is the normal force, and there is their weight. Those two forces combine to provide a centripetal acceleration. This is apart from dealing with the energy. So, normal force plus mg equals mv squared over r. I need to do this to figure out the velocity at the top so I can put it here to determine the normal force at the top. Now the math part, 1/2 times 24 squared equals 1/2 vt squared plus 9.8 times 20. Notice I dropped the m here because there's a mass in every term. You can use this to figure out vt. Over here, normal equals 74 vt squared divided by 10 plus 74 times 9.8. They told me that the mass of the person in the problem is 74 kilograms. Now, your numbers may vary. Actually, they say 73 kilograms. Assuming. I'm going to leave it 74. Your number's probably different anyways. So that's going to tell you the force from the track, from the seat on the person in the ride. Is this okay for the test? Sure. I would probably ask it harder than this. I'd probably try and have you figure out how fast you should be going so that you can at least make it through the loop, which we talked about, and you had a problem about it. The idea that you would have to know you have to be traveling fast enough so that you at least have some normal force or right at the threshold where you're going fast enough for your weight to act as your unbalanced centripetal force. Yes, sir.
So the centripetal force would have to be equal to 9.8 then? Whenever the top, like, whenever you're at the top.
What's centripetal force?
No, but your centripetal acceleration would have to be equal to that. You said force, so I just want to make sure we're clear because I'm recording. I don't want to say yes to the wrong answer. But yeah, if we look at this, the minimum centripetal acceleration to make the loop has to be 9.8 because that's the minimum to make it circular. You can have more than that, sure, but then the track has to push on you. Who else had a question? All righty. I did my algebra wrong. This should be negative. You too, guys. That should be negative. I did my algebra wrong. You guys watching, be careful. I did my algebra wrong. In looking at this question has two parts. Clearly, the more I pull back the spring, the faster the cars will be launched from the spring. Is that clear? Fair enough? Now, if I don't launch it fast enough, the cars won't make it in the loop. But it's not just about how high the loop is. And a lot of people think it's just about the height of the loop. Let me be kind of clear from the beginning that if I had a hill that was the same height as the loop, it would take more energy to run the cars through the loop than the hill. The reason is that when we talk about the hill, the cars don't have to be going on the inside of the loop and staying in uniform circular motion. In fact, we're worried that if you go too fast with the hill, you might fly off the hill like this. So in both of these, we're trying to figure out what it takes to maintain the circular motion necessary to be traveling in that path. So when the cars get up here, I want you to remember that the only way they travel in a circular path is if the net force is equal to the centripetal acceleration, meaning there has to be an unbalanced force towards the center that is great enough to deal with the inertia of the cars traveling this way. All right? The cars want to go in a straight line. Gravity will pull them down. We might need to pull them down faster than that to get them to travel in a circle. That's more or less what it comes down to. Now, this balance that we're talking about here has nothing to do with what it takes to get to the top of the loop. We can talk about this without talking about what you're doing to get there. Meaning, when I'm at the top there, two forces are acting on me. Normal and weight. If I want to find out how fast I have to be going to be in this loop with the forces that are acting on me, I would set the net force equal to mv squared over r. Now, every time I talk about this, students nod and say, yeah, that makes sense. But then when they're asked to talk about it, they balk at it and get all clammy and stop talking. But pay very close attention and you will understand. The left side is what is acting on the cars. The right side is how fast they're traveling. And it determines how much force is necessary to make the turn. here's the thing. If I go really fast, if I make v a very large number, then I'm going to need the weight of the cars and the normal force to both push on the cars to get them to curve. As I slow down and try and go slower and slower through this loop, I will find that the weight contributes the same amount to the force because the weight of the car isn't changing. But the track, this part, is less and less necessary to make me travel in the loop. Meaning mathematically, just the math part, if the velocity is getting smaller, on the left side, the normal force is getting smaller because the weight isn't changing. It is possible that I could reach a point where the velocity is small enough that the normal force is 0, and only the weight is carrying me through this loop. If I try to make the velocity any smaller, then the weight will be too much force to go through the loop, and I will fall out of the loop, meaning the radius will get smaller and my curve will be sharper than the loop. And this is because the normal force can't pull up on the car to deal with the fact that the velocity is smaller. Now, real roller coasters, the normal force can pull up on those cars. They are locked to the track in case the cars stop during a loop, which happens all the time. That's usually when the ride fails. It's a bad day for the riders, but most modern roller coasters are designed to deal with that. Now, what we're looking for is what is the minimum velocity that is necessary for me to travel through the loop safely. Now that minimum velocity means that there's a threshold where the smallest velocity represents the point at which the net force is only from gravity. Now in a real roller coaster, you would want to be traveling faster than whatever this value is. And that's what the problem says. They're telling you that they're going to have you travel with 13% more force to ensure that you can get through that loop, no trouble. Now, we're not here to do that part. We're here just to figure out what it takes to get through the loop. So we've done that now. If I want to get through that loop, I need to make sure that this balance is maintained. Now, what gives me the velocity at the top of that loop? That's the energy part of this problem. The energy part of this problem states that the energy I have here when I'm pushed up against the spring has to equal the energy that I have up here at the top of the loop. If I want to make the cars go faster, I compress the spring more. If I want to make the cars go slower, I don't compress the spring as much. I get to decide how fast the cars are going. And it's all based on how much I compress the spring. So at the bottom, I'll use my rules of energy to figure this out. I'm going to have elastic potential energy. I'm not going to have gravitational potential energy because I am at the lowest point in the problem. Oops, I don't want to do that. I want to do that. I'm not going to have kinetic energy because when I launch the cars, they're not moving. They're pushed up against the spring. They are starting from rest. So there's no kinetic energy down there. All I will have is elastic potential energy. But when the cars shoot themselves into the loop and they make it to the top of that loop, they are clearly above the reference level, so they will have gravitational potential energy. They have to be moving or they can't be traveling in a circular path, so there must be some amount of kinetic energy. But they're not pushed up against any springs or elastics, so there won't be any elastic potential energy. So what I'm looking to try and do is tune the system so that the elastic potential energy will provide me with enough energy to reach the top of the loop. In this case, h is going to be 2 times the radius of the loop, a diameter above the ground, plus the amount of energy I'll have due to my velocity. And to figure that out, I need to realize that the velocity is going to be based on the force. I need to resolve these two things. Meaning I need to figure out what K should be so that this system works. Now, I don't actually know how fast I will be going up there. I do know that how fast I'm going is going to depend on R and the mass and G. These are the kinds of things that are going to make this determination. So what I could do is I could eliminate mathematically the velocity between these two to try and figure out what the spring constant should be. So I'm going to pivot now from the physics to the mathematics part of this. They gave me some numbers to use here, and you know I don't care about the numbers all that much. I'll put the numbers that I have here, which are probably different than the numbers you were given. But I'm surprised that anybody has questions on this, since so many of you got like 90-something% on your mastering. I'm sure that you guys are experts at this. In fact, I should probably ask anybody who got 90% what to do next, because there's so many of them. But let's just assume that perhaps your 90% wasn't from knowing how to do this one. So it's 1/2 K times, the X in this case, they tell me is, where is it? How far they pull it back. Maybe they don't tell me how far back to pull it.
It was 6 meters.
6 meters.
Yeah.
Oof. 6 squared equals, we will need the mass. So they give it as 310. So 310 times 9.8 times 2 times, and I think the radius in my problem is 9.2, plus 1/2 times 310. All right, so here's the thing. I need to eliminate V. I'm not going to eliminate V, by the way. I'm going to eliminate V squared. So let's solve this for V squared real quick. V squared is going to be G over R, I believe. No, G times R. Sorry, didn't do my math right. G times R, which will be 9.8 times 9.2. There we go. I've now done the mathematics part. All that is left is for you guys to do the arithmetic. I'm not going to wait for you to do the arithmetic. I think that's something you can do at home. You guys can push buttons there. Whatever you get here, though, is not the answer, because the problem was a little more specific and said that, isn't there, they wanted 13% more, or is that a different problem? That was this one?
Yeah.
So when you get to the answer here, this will not be the answer. You need it to be 13% stronger than that. So you'll have to increase this answer by 13% to get the answer they're looking for.
You just multiply it by
1.13, yeah. I assume you guys can increase something by 13%. All right, that's this question for you. So let's take a look at what the problem is about. It's talking about an elevator lift that's going to lift roofing tiles, apparently along an incline at 75 degrees. So the roofing tiles are being propelled upwards by some force. Let's assume that that force is constant. If that's true, yes,
Can you state the definition of power?
yes. I can state it 3 different ways. Way number 1, power is the rate at which you do work. It is the rate at which work is done. Now, saying it like that, I am being very careful to throw the word rate out here. All rates have the same characteristic, time in the denominator. I've emphasized this already, so I'm just going to emphasize it a little bit more. Velocity is the rate your position changes, x over t. Acceleration is the rate at which your velocity changes, v over t. So power is the rate at which work is done, which means power is work over time. You could also state that power is the rate at which energy is consumed. I'm not going to write all that here, but a 60-watt light bulb is consuming energy at a rate of 60 watts. The unit must be a joule per second, right? The unit of work is the joule, the unit of time is the second, so the unit is joules per second, which we call watts. That's Sir James Watt. Now, if you consider the definition of power for just a minute as work over time, I would encourage you to recognize that we can expand the definition of work to be the calculation of work, force times displacement times the cosine of the angle. And since we can multiply or divide in any order we wish, I can group these together to get force times delta x over t times the cosine of theta. This suggests that if you have an object moving at a constant velocity, the power requirements are force times velocity, which is a second way to calculate power. Now, this is the best way to do this problem. They're asking for velocity. They tell us the power is 700 watts. If we can figure out the force necessary to push the box up the ramp, then we can figure out what velocity they must be moving up the ramp. The force necessary to push the box up the ramp has to be equivalent to mg sine theta. That's got to be the force necessary to push the package up the ramp. So, power equals mg sine theta times v times the cosine of 0 degrees. They give the power 700. The mass was 25 times 9.8 times the sine of 75 degrees, all times v. This will not get you the answer that mastering wants. This will get you the actual velocity up the ramp. They want the component upwards. So they'll have to multiply by the cosine of 75 degrees. All right. The bell rings in like 30 seconds.
Wait, so you said multiply by the cosine of 75?